look at that. Okay, reset. Vector fields. Beep. So we have the concept of function. Going back to algebra. And back in algebra, you had an input, typically called it x, which a real number. And you had some process that you called f that would give you an output, f of x, which was a real number. All right? And you could visualize the function y equals f of x by putting your inputs on one axis and the outputs on the other, and you would have your curve x comma f of x. All right, and then you did your calculus and all that good stuff with this kind of function. Then you had parametric equations. Parametric equations, your input was t. You could think of that as time. And you sent that over to a pair of functions, x of t, y of t, which would then produce a point x comma y. And so this is a way of generalizing the concept of functions in order for you to be able to trace out more interesting curves on the plane. So for any particular value, t naught corresponded to a point x naught, y naught, where x was x of t naught and y was y at t naught. Okay? And then at the beginning of Calc 3, we kind of packaged these together and got vector valued functions. So vector valued functions, your input was a real number t, and your output was a vector r of t. And what we could do is we would place that vector in standard position. So we would plot the vector here in standard position. And then if I looked at the terminal point of that, that would help us trace out curves in either the plane or space. Okay, so inputs were real numbers, outputs were vectors. And throughout all of this, we've got the function condition that each input gives you only one output. Then we spent a couple of chapters talking about functions of several variables. So functions of several variables, you started with a point, either in 2 space or in 3 space, and then you associated that with a real number, f of x, y, or f of x, y, z. And in the case of function of 2 variables, z equals f of x, y, you could go back to what we did in algebra and just have the inputs, the domain, in this case being in the xy plane, the outputs, so this would be the input down here, these would be the outputs, and then you would graph these things and get surfaces. All right. So what's a vector field? A vector field combines vector valued functions with functions of several variables. So the domains for vector fields are going to be points, either in 2 or 3 space, and the range, the outputs, are going to be vectors. So that's what a vector field is. It's the combination of these two things. So your inputs are going to be points, xy or xyz, And your outputs are going to be vectors. So we'll say we'll have a capital F. So capital F of xy or capital F of x, y, z. Now, unlike vector-valued functions, where we always pin the tail of the vector at the origin and then use it to graph out a curve, the way we're going to graph vector fields is we'll graph the initial point to be the input point. So when we go to graph a vector field, say it's a two-dimensional vector field, so we've got a vector f of x, y. Then what we would do, let's say we have a point, say x naught, y naught, then we'll use that as the initial point to plot the vector f of x naught, y naught. Okay, so we're going to actually plot the vectors with the initial points being the inputs. Okay, because we're taking points in the plane and associating a vector with it. Now, the classic application for this kind of thing are like velocity fields. Okay. So, for example, like, if you type in like wind velocity map, so like here's the current wind direction. So at each point, they indicate a vector, which is telling you the direction of the wind. So we're getting these winds out of the south here. Typically, when we write vectors, the length of the vector indicates the magnitude. Here, they're using color to indicate the magnitude. So if you have a green arrow here, it means the winds are between 1 and 10 miles an hour. Yellow, 11 to 15, and so on. Right, so we can look up here, Cuyahoga County, and go over to Lake County. Can we get to Lake County? There we go. Okay. So velocity fields. And we'll see other applications as we move along. So let's talk about how we can, once again, visualize these things, because they are velocity fields. This is a, there's always the partnership between algebra and geometry and calculus, and so this is a very geometric thing. So, for example, if you wanted to graph this field, say by hand, and wanted to plot vectors by hand, so there's your point x and y. What you would do is you would just plug in different values for x and y, and then you would get your vector out. So if we had, say, x and y here, notice our field is just y comma 0. So for example, if you plug in some points like 2, 0, 0, 2, negative 2, 0, 0, negative 2, each of these points would then spit out a vector. But notice the vector, it just gives you the y coordinate in the x component. So this would be the vector 0, 0. This would be the vector 2, 0, 0, 0. Negative 2, 0. And you can go over here and plot at the point 2, 0, we have the vector 0, 0. At the vector 0, 2, we have the point 2, 0. At 0, 0, or excuse me, negative 2, 0, we have 0, 0. And so on. Okay, so if I think about it, any point that's on the x-axis, would have a y-coordinate of 0, and that would just get mapped to the vector 0, 0. So if I think of this as sort of a velocity field, any point here along the x-axis, we're going to have no velocity at all. That's where things are still. And the further I move up in the y direction, if y is bigger than 0, the bigger the magnitude I'm going to have. So, for example, anything here at altitude 2 is going to have the vector 2, 0. So anything here at altitude 2, if the y coordinate is 2, we're going to have the vector like this. If I go up to like 5, it'll have 5, 0. You follow? Now if I go below the y-axis, all these y values are negative, which means they're going to be pointing the opposite direction. They'll be pointing to the left. And the further I go down, in absolute value, the bigger the y component. So in magnitude, the bigger the vector. Right? You see how this is getting plotted? And you see how we're getting the picture here? Now there are a couple of apps I got a couple of links here to some GeoGebra, two-dimensional, three-dimensional vector field plotter. And what you can do is go into GeoGebra here. They're Vx and Vy. So this is the vector field. So you would just plug in, for us, we just had Vx, y was y. That's the x component of the field. And the y component of the field. And then what you can do is you can increase the number of samples you get, and then you can increase the length of the vectors. So you can kind of see what's happening here. This is called a shear flow. So if you have a shear force, you've got like two layers, and one is sliding one way or the other. So you can see here at the top what's going on with that. So here, once again, the length of the vector indicates the magnitude. So the further away you get from the x-axis, the more force you've got going on. In the top, we're heading this way. Down below, we're heading the other way. Okay. Channel flow. Let's look at this one. 0, and then sine of pi x. So once again, just kind of looking at these fields here. This is called a channel flow. Can you see why it might be called a channel flow? So you've got here these sort of well-determined channels where things are flowing. So this is heading down, heading up. This is up but stronger, and then down. Let's zoom in here. Let's look at negative 1 to 1. Just kind of zero in on that. And no, X max would be 1, Carl. Thank you. There we go. Try to clean this up a little bit. There you go. You see the channels? You got a down channel and then an up channel. And then, you know, since it's sine of pi x, anytime pi is a natural number, or in general an integer, anytime x is an integer, you'll have 0 flow. So it would just zero out, and then that would be the start of a new channel. So you've got these channels every integer of pi here. Here's a down flow and then an up flow. So but they have them in these channels. And then at every pi units, there's nothing, right? So that's sort of the division between the two channels. All right, turns out we've actually seen vector fields before. Anytime we take a gradient, we've got ourselves a vector field. All right, now you're going to see this, once again, we're sort of running out of variables. That's how far you are along in math. We're starting to run out of variables. So this is phi. This isn't the spherical coordinate phi. This is going to be our generic go-to for a scalar function. So if you take a scalar function and take the gradient of the scalar function, that's a gradient field. So we have seen examples of vector fields before. Phi is called a potential for that gradient field. Right? So for example, find the gradient field associated with phi of xy equal inverse tangent of y over x. This may look familiar to you from a previous take-home assignment. But if they want the gradient field, they just mean to take the gradient. The gradient is a vector field. It took a point and matched it up with a vector. So once again, how do you get the gradient? You take the partial derivative of phi in the x direction, and that's your x component. You take the partial derivative of phi in the y direction, and that's your y component. So the derivative of the inverse tangent of something is 1 over 1 plus that thing squared times its derivative. So as a review here, if I wanted phi x of xy, I'd be taking the derivative with respect to x of the inverse tangent of y over x. So the derivative of the inverse tangent of something is 1 over 1 plus that thing squared times the derivative of that thing. And what's the derivative of y over x? What's that work out to be? Minus y over x squared. So I can multiply the numerators here. Minus y times 1 is minus y. When I multiply the denominators here, I'd have x squared times 1. And when I multiply the x squared here, drop out. So I get minus y over x squared plus y squared. So that's my my phi x. Now I need to get my phi y. That's the derivative with respect to y of the inverse tangent of y over x. So once again, the derivative of the inverse tangent of something, 1 over 1 plus that thing squared, times the derivative of that thing, in this case with respect to y. And what's the derivative with respect to y of y over x? That's just 1 over x. Good. So this would be 1 over 1 plus y squared over x squared times 1 over x. Now if I wanted to wipe out this little denominator here, I'd want to multiply by another x over x, and I would get x over x squared plus y squared. So it's been a while since you've done partial derivatives, unless you looked at the Jacobian video on Friday. No, we just need one more x here, Zeron. So if I multiply this x through, I would get an x plus a y squared over x, so I would just need to multiply by another x. Yeah, okay, yeah, no worries. Yep. All right, so now you put them together, and boom, there's your gradient field. All right. So this goes back to, chapter 15. We had a function f of xy, and then we went to the gradient f of xy. So these were actually vector fields. So we've got the following. All gradients are vector fields Okay. A natural question would be, are all gradient or all vector fields gradients? You see how that would be? Yeah, and the answer is no, and we'll talk about that more on Friday going into next week. Okay? So gradients are a particular type of vector field, but not all vector fields are gradients, are gradient fields. Okay, here's a couple more examples with help from a graphing utility, sketch or otherwise describe. So here we've got, the first example, we're just looking at one component and how it varies with one of the variables. So this is where we're trying to get a little more robust here. Radio fields and rotation fields. And these fields are sort of important in the grand scheme of things. We start talking about what these things do. Let's dial these in. So the radial field XY. Put that in there. Let's do like these on squares. There we go. Let's dial this back. Oh, that's a little obnoxious. And there's a radiate field. So if you had to try to describe what's happening in this picture, right? You look at how the vectors are going, what direction they're going. Like if you imagined this was sort of a wind direction map, right? If you were right here at the center, you'd be completely still. But the further you went out, what would happen? Like if I were over here, what direction would I be pushed? Yeah, outwards. Perfect. That's a great word. Right? Because no matter where you are, you're always being pushed outwards. Okay? So this has a sort of spreading out kind of a feeling. All right? This would be like a what they would call a source. Right? You've got this wellspring here. So the further out you go, the more outward push you're going to get. Okay? Compare that to a rotation field, y comma negative x. You see why this is called a rotation field? Because if I imagine I was there, I would be getting pushed this way, and then I would be getting pushed this way. And you can almost follow the trajectory all the way around. Yeah. So these two, and we'll come back to this. We'll come back to this later. Yeah. This is divergence and curl. So this is the concept of divergence. So spreading out, and then curl, which is the rotation. So these are two big ideas in this unit that we'll see again and again and again. Okay, we had unit vectors back, the first day of class. We talked about unit vectors, so you can have unit vector fields. So a unit vector field is a vector field where all the vectors have length 1. Okay. So basically, you can think of that as a direction field, because that's just giving you directions only. So for example, if you looked at these two, if I looked at the norm or the magnitude of either of these two fields, well, how do you get the length of a vector again? It's a callback to what theorem? Yep, Pythagorean. You square the components, add them up, take the square root. Notice here, you would get y² plus minus x², but that would be the same. So these have the same magnitude. So at any given point, these two vector fields, they have the same magnitude. What's different is their directions. And we could put this in here. There it is. So all those vectors have length 1. They're unit vectors. So that would be the direction field for this rotation field. It's clockwise circulation, right? So we're going clockwise there. And we could change it back to look at the other one. And those are all unit vectors there. Okay? So you can normalize the vector fields to take out the magnitudes and just leave you with direction. Inverse square field. These are very popular in a lot of applications. There's a lot of things that drop off by 1 over the distance squared. So for example, the gravitational force, luminosity, these are things that step off in 1 over distance squared. So if you take the magnitude of your field and it's some constant divided by x squared plus y squared, it's called an inverse square field. So what's actually happening here, where does this come from, is this vector field r of xy is xy. This is basically your position field. Because it just gives you the vector based on your position. Okay. So if we take the magnitude of this thing squared, that means we would have this square root squared. You just get x squared plus y squared. So what this is really doing is this is really measuring your distance squared from the origin, right? So if you're at a point here, xy, the magnitude of this squared is just the distance to the origin squared. Okay, so you're still looking at 1 over the distance squared. So an inverse square field, the inverse comes from the fact it's a reciprocal, and then it's some constant. So the strength of the field is inversely proportional to the square of the distance to the point to the origin. Right. So for example, if you wanted to show something is an inverse square field, then you calculate the magnitude. And as we reviewed, the way you calculate magnitude is you square components, add them up, take the square root. So you take 2x over x squared plus y squared to the 3/2 squared, plus 2y over x squared plus y squared to the 3/2 squared. And when you square a fraction, you square the numerator, square the denominator. When you square the numerator, not only do you square the x, you got to square the 2. What's going to happen when you square this denominator? You've got a 3/2 powered squared. What do you do with those exponents? Yeah, you multiply them. You would just get cubed out of this. Whoops. And you've got the same denominator, so you can just add your numerators. Whoops. It's still acting a little goofy. So you can factor out that 4. And now you can see what happens here. You get the square root of 4, which is 2, and the square root of this. There it is. So that's an inverse square field. inverse square field. The strength of the field, the magnitude of the field, is directly proportional to 1 over the square of the distance from the origin. So as the further away you get from the origin, the more it drops off. Put that, whoops. Put that there. Put that there. Put that there. Put that there. Oops. So as you can see, as you step away at the origin, you've got, you know, crazy long vectors indicating huge field strength. But as the further out you go, you see the smaller these, the shorter the arrows are. So it's dropping off. Find and simplify a formula for the unit vector from this and show it's a unit vector. So I'll leave those machinations to you. I guess I do want to remind you, how do you divide a vector by a scalar? So here's our vector. And I want to divide it by this scalar. How do you divide a vector by a scalar? You divide each what? You divide each component, right? So it goes component-wise. So I'll leave that algebra to you to work through. That should be your direction field, and then you can confirm that it's really, truly magnitude 1. Okay, so once again, you want to be going back and reviewing some of these basic vector properties. Extensions to 3-space. Well, how do we always extend stuff to 3-space? For functions of several variables, we just tacked on a what? And in vector valued functions, we just tacked on a z. That's it. So you can, in 3-space, here's a couple examples. Rotation fields and inverse square fields. And once again, there's a little applet here. And these are linked, like I said, in the Blackboard site. So if you go to the Blackboard content, there's links to them here. And I encourage you to play with it. Maybe you'll find, I mean, these are the ones I used last year. I haven't looked to see. I don't know if Desmos can do these nicely. But here's a 3-dimensional field. So they call the components P, Q, and R. So let's look at this rotation field, 2z minus 3y. Three x minus z. Y minus 2x. Now you can actually just grab this and move it around. It looks like a jumbled mess, but you should be able to orient it to see some rotation. Let me make sure I typed it in right. Yeah, you can see the rotation there, I think. You can get a sense of the rotation there. It's like a swirling vortex. And once again, well, that's the notion of there's a curl involved there. Inverse square field, we can just sort of bump up the last one we did. This will be minus then, so this will be pointing in towards the origin. Wait, did I do a square root? Square root. Put this in here. Put that there. let's see. I guess we forgot to cube these here. There we go. So there's an inverse square field. So we can. Yep. So move the scale in here to see a little bit better. Everything's pointing inwards, right? No matter how you look at it, everything is pointing inwards towards the origin. Okay. And just like in 2 dimensions, you can create 3-dimensional vector fields by taking the gradients of 3-dimensional scalar functions. So here's phi of xy. Phi of xyz is 1 over the square root of x squared plus y squared plus z squared. Now once again, you might recognize what phi is doing. The square root of x squared plus y squared plus z squared, what's that calculating? If you have a point x, y, z, what does this calculate? Yeah, this calculates the distance. Yeah, that's the distance to the origin. So that's your distance d. So this is the reciprocal of that. Okay? Now, if we're going to start taking derivatives with this, we would likely rewrite this as x squared plus y squared plus z squared to what power? Minus 1/2. And what's nice about this, we've seen this before, there's symmetry everywhere. This function's completely symmetric with x, y, and z. So once I can find phi x, I can just permute the letters around to get phi y and phi z. So let's go ahead and do that. What would phi x be? Well, you'd be taking the derivative of something to the minus 1/2 power. So that'd be 1/2 times that something to the what power? Minus 3/2 times the derivative of that something, in this case with respect to x. And what would this work out to be? What's the derivative of this? Yeah, the 2x. So we get the 2's would cancel. I'd be left with the minus x, and then I could write this in the denominator. And then for phi y and phi z, I would just, like I said, permute the letters around. I would just replace x with y. And then the same with z. Once again, exploiting that symmetry. Yeah, it should be 3/2 down here. Thank you. Yeah, that's correct. Yep. And so then for the gradient field, you just have your x, y, and z components being the x, y, and z partials. And there it is, which is exactly this field here. So the inverse square field f is actually the gradient of phi. And here's a recipe for 3-dimensional rotation fields. Pick your favorite non-zero vector v and let r, once again, this would be the position field here in 3 space. Compute v cross r, and that would get you a rotation field. So what's your favorite 3-dimensional vector here? 1, 2, 3. And then r, position vector, x, y, z. let's remind ourselves how to take that cross product. We can abuse notation here. Remember doing the old cross product? Cross product's back. Everything's back pretty much. Everything's back in this except like Lagrange multipliers. Everything else comes back. So we're going to take I here and sort of imagine looking at the little determinant we get here. So we'd have 2z minus 3y minus j times, we would imagine, ignoring those, we'd have 3x minus z. And then for the k component, we would imagine, ignoring that, we'd have 1y minus 2x. Yeah, well, we got to do the minus here. Yep, it's going to be z minus 3x in the final. It's because the way I'm doing the expansion of minor stuff, right? Oh yeah, this should, yeah, I was thinking it, yeah, so right, yeah, this should be z minus 3x. Thank you. I got ahead of myself. There we go. So it'll be 3x minus z then in the final. So the final field would be 2z minus 3y, 3x minus z, y minus 2x, which I think that's the example we had up here. Right? There it is. So that's actually the vector I used for that one. But you can do that for any vector. Like, you know, play around with it. Like, what if you use like I hat? What if that's your vector? Or j hat? You know, and calculate those cross products. Well, we specify a non-zero vector, because if it's all zeros, then you get nothing. You just end up sitting there. But yeah, like, you know, what would happen if you chose I hat? What would the rotation look like? So, you know, once again, I mean, there's homework problems to work on, right? But I think what's valuable here is playing with these tools. You know, getting a good sense of what's going on. All right. So tomorrow we're going to start line integrals. So we're going to generalize it, the integral. And we'll see what that can do for us. But for some reason I'm starting a coughing jake here, so I'm going to tune out. Enjoy the sunshine. Have a great rest of your day. Thanks for being here, folks.